In this question, we have a weight, which is being suspended in the air by two ropes, and we are asked to find the tension in both ropes. Now, the first thing I always do is draw a free body diagram. We will draw a point which represents the weight, and then we will draw the tension force from rope 1, which I will call T1, the tension force from rope 2, which I will call T2, and then the force of gravity, which is pushing down on the weight. And now it's really important that you recognize that the tension vectors T1 and T2 are at an angle because the ropes are hanging from an angle. And now if you're a little confused about why I drew the angles where they are, all you have to do is use the Z theorem, which states that if you have two parallel lines, the alternate angles are always equal. So now we have our basic free body diagram, but what you have to recognize is that the tension vectors, T2 and T1, are at an angle, which means they can be broken down into their x and y components. So looking at T2, we will have a T2x component and a T2y component. The same goes for T1. We will have a T1x component and a T1y component. And now how do we find T1x, T2x, T1y, T2y? Well, if we do some vector addition and set up right-angled triangles, we can use trigonometry to solve for our different x and y components. Let's start by solving for T2y. We can use sine theta is equal to opposite over hypotenuse. All we have to do is replace the opposite side with T2y and the hypotenuse with T2. Then we rearrange and isolate for T2y, and we find that T2y is equal to T2 sine 20 degrees. Now let's find T2x. We will use cos theta, which is equal to adjacent over hypotenuse, replace the adjacent side with T2x and the hypotenuse with T2, rearrange and isolate for T2x, and we find that T2x is equal to T2 cos 20 degrees. Now we can do the exact same math to find T1y and T1x. T1y is going to equal to T1 sine 30 degrees, and T1x is going to equal T1 cos 30 degrees. So now that we solve for the x and y components of our tension vectors, we can start setting up our F net equations. Since we have forces acting along both the x and the y axis, we will need to solve for an F net x and an F net y. F net x is the sum of all the forces acting along the x-axis. So F net x is equal to T2x minus T1x. T1x is negative because it's a vector that points to the left. And now what you have to recognize is that F net x is equal to 0. And that's because the weight is not moving. So there's no net force acting along the x-axis. And with that, we can rearrange this equation and we see that T1x is equal to T2x. And for now, I'll just leave that equation just like that, so we can move on and make our F net y equation. F net y is the sum of all the forces acting along the y-axis, which would be T1y plus T2y minus the force of gravity. And remember, the force of gravity is negative because it's a vector that points down. And just like with F net x, F net y is equal to 0. And that's because the weight is not moving along the y-axis. We can also replace the force of gravity with mg, because the force of gravity is equal to the object's mass times the acceleration due to gravity. Now what I want to do is replace T1y and T2y with the x and y component equations that we solved for earlier. I will quickly simplify this equation, and what we're left with is 0 is equal to T1 sine 30 degrees plus T2 sine 20 degrees minus 98 newtons. Now we have two unknown variables, T1 and T2. So what are we supposed to do? Well, let's look back at our F net x equation. If I replace T1x and T2x with their x and y components, then we get T1 cos 30 degrees is equal to T2 cos 20 degrees. And what I can do is rearrange and isolate for T1. Then I will simplify the equation, and we find that T1 is equal to about 1.085 times T2. And now what we can do is plug this value of T1 into our F net y equation. And the reason we do that is because now our F net y equation will only have one unknown variable. So we can solve for T2. All we have to do is replace T1 with 1.085 T2, and then do some math to simplify our equation, rearrange and isolate for T2, and we find that T2 is equal to about 111 newtons. So now we have the tension in rope 2, but how are we going to find the tension in rope 1? Well, we know that T1 is equal to 1.085 times T2. So all we need to do is plug in our value for T2, and we find that T1 is equal to about 120 newtons. And so now we have the tension in rope 1, which is about 120 newtons, and the tension in rope 2, which is about 111 newtons. Now this was a difficult question. It challenged you to draw free body diagrams, make F-net equations for the x-axis and the y-axis, and to solve for the components of the tension force vectors. Give my other force questions a try to keep testing your knowledge.